Okay, let's do it.
Is the answer 6.15?
I have no idea, but it's the square root of, it's square root of 4/3. It's 2 over the square root of 3, or 2 square root of 3 over 3 if you rationalize it. Either way.
Who wants to rationalize it?
I know it. That's so last century, you know? Okay.
Rationalizing.
So here we go. We want to maximize this area of 2xy. Given that the y is equal to 4 minus x squared, okay? If the point is on this curve, the y-coordinate is 4 minus x squared. So what we want to maximize is 2x 4 minus x squared. Now let's get some restrictions on x. Let's get some endpoints here. Endpoints on x. X is going to have to be, what are some restrictions on x? It's got to have to be greater than or equal to what?
2.
What? No, it can't be greater than or equal to 2, 0.
Oh, 0.
But less than or equal to 2, because it has to be inside the parabola, okay? So those are our endpoints. We have our quantity to be maximized or minimized in terms of a single variable. That's what we want, okay? Let's take the derivative to find the critical values. I'm going to multiply this out. I'm going to have 8x, take the derivative, 8, minus 2x cubed, the derivative of which is 6x squared. Is that it, Trent? Is that where you made a mistake?
No, I think I didn't take the derivative initially. I did 8x minus
2x cubed. That's okay.
And got...
And you find the derivative of
No,
that?
I left the x. I don't know.
All right, well, you had to take the derivative of it. Now, set the derivative equal to 0. This is how we find our critical values. Solve for x. Add 6x squared to each side, or solve it any way you want. Divide by 6, you get 8/6 4/3. Take the square root. Now it's plus or minus, but we said x had to be greater than 0. So I'm only going to take the positive root, which is 2 over the square root of 3. And like I said, if you want to rationalize it, fine. Okay, I kind of like 2 over the square root of 3 better even, but either way, yes?
I just had a question. On the test, are we going to have one with the graph like that and then one like the other one we just did?
No. I can't tell you specifically what you're going to have. You're going to have 2 problems on the test.
It's easier with the graph.
Yeah, I don't know if I don't think I give you any graphs, though. I don't think this will be one of the
Are we gonna do
problems.
the cow thing?
What's that?
The cow thing?
You may have a farmer cow thing, yeah, you may.
That one confused me. This one makes more sense than that.
What's that?
This one makes more sense than the cow thing.
Well, okay.
Just to take that into consideration for one.
Well, the test is already made up, so
So go back.
fix it. It's already fixed. All right, so x is equal to 2 squared root of 3 over 3. Now the question is this a relative max or a relative min? And we should test the endpoint. So take the second derivative. Second derivative is negative 12x. When x is 2 squared root of 3 over 3, substitute it in here, you get a second derivative that's negative. Concave down, we have a relative max. Okay? Go ahead. Go ahead.
Can you repeat that last part?
The second derivative is negative 12x.
Yeah, you put the x in there.
When x is 2 squared root of 3 over 3, substitute it in here for x, you get a negative value. And that tells you the curve is concave down, and we have a relative maximum.
You got
And
the
that's what we're
12x
looking
What
for.
would relative max,
Good.
Excuse me?
what would relative maximum be?
The max is, I haven't done that yet, this is where it occurs. What is that maximum? Let's check it out. Well, check out the endpoints first of all. When x is 0, what do we get for an area? 0. When x is 2, what do we get for an area? 0. So again, we have minimum values at those points. Those are not the solution to the problem of maximizing the area. So what is the maximum area? The maximum area is equal to 2x 4 minus x squared, or 2x times y. If you want to take this value and find out what y is at that value, that's okay. Or you can substitute it in here. So it's 2x 4 minus x squared. And what is x squared? 4/3. This will be the maximum area, whatever that happens to be. I might as well do it out. So you get 4 square roots of 3 over 3. This is 12/3 minus 4/3. That's 8/3. That's 32 square roots of 3 over 9. That would be the maximum area of that rectangle inscribed inside that parabola. Okay?
That's the area at x equals 2 square roots of 3
Over 3.
over 3.
That is
That's
correct.
the max area of that rectangle?
That is correct.
But you would have to still find the y, correct?
Maybe, I don't know, if
For
I
the-
ask for the maximum area, that is the maximum area. On the test, I'll probably ask for the x value and the maximum area.
I'm
So you
sorry.
wouldn't even need y.
I'm sorry, the negative 12x real max, that's from the y equals 4 minus x squared?
No, this is from taking the second derivative of our
Oh,
first
that's
derivative.
just to see if it,
Yeah.
where,
That's to see if we have a max or a min.
got it.
Carolina?
In the parentheses where it says 4 minus 4/3.
Yeah.
Shouldn't that be squared?
I squared the x. X squared is 4/3.
Oh,
Damien?
So to find the max area of that rectangle, you have to find the derivative, find the critical values, and then take the critical value of x by looking at the endpoints to make sure it matches that.
Well, you take a look at the endpoints to make sure what you do have is the absolute maximum. See, I know I have a relative max by the second derivative test, but do I have an absolute maximum? I'm not sure until I test the endpoints. It's possible that what I have, what calculus tells me is the maximum is not the absolute maximum in that interval, okay? See, it's conceivable that what you have is something like this, and this is the interval. Over this interval, the calculus gives you this critical value and this critical value. Well, this is a relative max, and this is a relative min, but if you want the absolute minimum, you got to go over here at this endpoint. The calculus is not going to give you this point. Okay, it'll only give you the points where you have horizontal tangents. And the absolute maximum is this point over here. The calculus is not going to give you that. So that's why you should test endpoints, to make sure that what you have is indeed the absolute max. And that's what happened here. By testing this with a second derivative test, I got a relative max, and then looking at the endpoints, endpoints are not even close. The endpoints give me 0 for areas, which are clearly not maximum values. So I know I have the solution. You guys ready to do another one?
How about the minimum? What's the
Minimum would be 0,
0.
okay?
Because it's the endpoint.
At the endpoints.
Yes.
Yep. I'm going to give you another one, all right? I'm going to go back to Farmer Brown, okay?
Now, the minimum could also be the, if it's less than 0, and say, if it's something like this, but it goes into the negatives.
Yeah, it depends on the
It
problem.
really matters on the problem.
If you had a real life problem, oftentimes you can't have negative numbers for solutions. I mean, sometimes you can. But you have to be careful, and that's why you set up the endpoints to define what your possible values are.
Awesome.
All right, another Farmer Brown problem. Here we go.
Farmer Brown.
Farmer Brown is going to enclose a rectangular area. Okay. Now, Farmer Brown knows how much area he wishes to enclose. He wishes to enclose 10,000 square feet. Okay, that's the area. We know that. Okay. But the material that he uses for the lengths is more expensive than the material for the widths. For some reason, he's going to put a gate here and a gate here. Okay, so he's got 2 gates, so it's more expensive along those 2 sides. Okay, so let's say this side is $2 per foot, and this one is $2 per foot. Oh, shoot. $2 per foot. And let's suppose these two sides are cheaper, he doesn't need the thickness, or he doesn't have to put a gate, or whatever the reason is, and these sides are just $1 per foot. Okay? So, here's what I want to know. What dimensions should he use to construct his rectangular enclosure to minimize the cost? We want to minimize the cost. You guys do it. You guys do it, and there you go. Call this X, Y. So you minimize the cost.
So we're looking at parameter, pretty much.
Well, you want to minimize cost, that's what I'm going to tell you. And I know how much area I have to enclose.
Minimize cost plus the best area? Or
No.
Just
The
minimize-
area is 10,000. That's it. Whatever you construct here, it's going to have to enclose 10,000 square feet of area. But I want to minimize the cost. Now, you could make a square out of it, and each side would be the square root of 10,000, or 100. But would that minimize the cost?
So that's-
But it can't be zero, right?
What's that?
It can't be zero.
There's no way you're going to construct this enclosure and have a cost of zero.
No,
No
not
way.
the cost, the, one of the sides.
Can't be zero, no. You not get an area of 10,000. You have to have an area of 10,000 square feet.
This one's tough.
Hmm?
This one's tough, a little twist.
Twist?
You didn't give like a y equals, like you didn't give like,
I know, I'm leaving it up to you. I'm leaving it up to you. What you gonna do? Who sings that? That's,
No idea, but you probably should stop recording.
Just press pause it, so it's all.
You'll have